Hello guys, welcome to my channel. In this video, we'll discuss about microservices, how and why IT moved from monolithic architecture to microservices architecture. So first, I'll start with what is a monolithic architecture, what were some of its drawbacks, and why industry slowly shifted from monolithic architecture to microservices architecture. Then I'll explain in detail what are microservices and its benefits. Then we'll also discuss about how do microservices communicate as well as some of the challenges that are introduced as part of microservices. So let's get started. The traditional way of building an application was an all-in-one application called monolithic architecture. So monolithic architecture is like a big container wherein all the software components are assembled together and tightly packaged with the common code base and a common database. For instance, for building a ride sharing application like Uber with monolithic architecture, all the components like passenger management, driver management, payment, and trip management will be part of single code base. Also, there will be one executable file or directory for deploying the whole application, which makes deployment easier. Since a monolithic application is a single centralized unit, end to end testing can be performed faster than with the distributed application. Also, since everything is part of a single code base, it is easier for developers to debug. Everything is developed, deployed, and scaled as one unit. Monolithic applications can be effective until they grow too large, which leads to some of the challenges. All the application is part of one code base, so when the application grows, it becomes difficult for teams to understand and manage such an extensive code base. Also, if during peak hour number of trips are increasing and we want to scale trip management service, it is not possible to scale one part of the application. Instead, whole application needs to be scaled, which leads to high infrastructure cost. Another major challenge is lack of reliability. If there is an error in any module, it could affect the entire application's availability. Another issue is of tight coupling in the modules, which means developers from different teams needs to pay attention not to affect the work of any other team. Such an application is constrained by the technologies already used in the monolith, which means different teams can't decide independently on what technology stack or language they want to use for their modules. Any change in the framework or language affects the entire application, making changes often expensive and time consuming. Let's say our application is written in Java, and if another module needs to be built named vehicle management and its team want to write the code in Python, it is not possible because they are restrained by the already used language in Monolith. Another major drawback with monolithic architecture is that making a small change in one part of the application, say driver management, the whole application needs to be tested, which means making a small change in single function require compiling and testing the entire platform. It is also an obstacle to frequent deployments. In order to update one component, you have to redeploy the entire application. There is a chance that components that have not been updated, like passenger management, will fail to start correctly. As a result, the risk associated with the redeployment increases, which discourages the frequent updates. So, the solution to all these problems was a microservices architecture or microservices. Now, what exactly is microservices? In a microservice architecture, the whole application is divided into small independent services. These services are divided based on business logic and keeping single responsibility principle in mind, which means one microservice will handle one business logic or domain. For example, payment logic or passenger management are two separate concerns. Therefore, they will form two separate microservices. Also, each microservice has its own database. There are cases where shared database is used among microservices, which is shared database per service pattern, but this is considered to be an anti-pattern because when using a shared database, the microservices lose their core properties like scalability, resilience, and independence. Another important characteristics of microservices is that they are loosely coupled, which means updating, testing, deploying, and scaling occur within each service independently. Now let's discuss the benefits of microservices. Making changes to legacy applications has risk attached, as changing one process could negatively affect another. But with loosely coupled microservices, updates can be performed independently of the rest of the application. This then leads to quicker application development and version rollouts so that companies are able to fail fast and stick to agile product timelines. Another one of the main advantage of microservices is flexible scaling, which means that if the microservices reaches its load capacity, new instance of that service can rapidly be deployed to the accompanying cluster to distribute the load. Also, adopting microservices often goes hand in hand with DevOps since they are the basis for continuous delivery practices that allows team to adapt quickly to user requirements which result in frequent and faster release cycles. Since microservices are individual units, they allow for fast and easy independent development of individual features. Another important feature for microservices is that they are highly reliable, so you can deploy changes for a specific service without the threat of bringing down the entire application because all the services are independent of each other. For example, you can go for the deployment of trip management service while other services are still working and are not affected by the deployment. Moreover, teams can experiment with new features and roll back if something does not work. This makes it easier to update code and accelerates time to market for new features. Plus, it is easy to isolate and fix faults and bugs in individual microservices. Additionally, microservices architecture also allows team the freedom to select the tools, frameworks, and languages they desire. Different teams can choose different tech stack to work with. Now, an important question is how do services communicate with each other? Because in a monolithic architecture, all the classes or modules of an application are in the same process and usually invoke each other through method calls. But when an application consists of more than one service, one microservice will have to request or pass some data to another microservice or notify one or more other microservices that something has happened. The outright leader, when choosing how microservices will communicate with each other, tends to be the HTTP. The client sends a request and waits for a response from the service, so that means client code block their thread until the response reach from the server. The problem with the synchronous communication is tight coupling between the services as one service is continuously waiting for other service response. Technologies like REST, SOAP, RPC, and WebSocket are example of the most widely used synchronous communication technologies. Another way how microservices can communicate is via asynchronous calls. In an asynchronous interaction model, the requester need not wait for the response. One way to achieve this is using HTTP communication but keeping a separate thread for polling and let the main thread continue. Polling thread can keep on checking with the service if a request has been processed or not. With this approach, we keep the services isolated from one another and the coupling is loose. The downside is that it creates extra HTTP request on the second service. It is now going to be polled from the outside until the request is completed. This introduces complexity on the client as well, since it now must check the progress of the request. Another communication pattern we can leverage in microservices architecture is message based communication. Unlike HTTP communication, the services involved do not directly communicate with each other. Instead, the service push the messages to a message broker or a queue that other services subscribe to. Message queues have an only once delivery goal, which means message queues only deliver each message once to a single consumer. Message queues process on a first come first serve basis. They may not deliver in the same order in which the messages are queued. Example of messages queues include RabbitMQ and ActiveMQ. Yet another way of communication is streaming integration. When streaming integration is implemented through a streaming broker, it is architecturally similar to messaging integration in terms of decoupling microservices. In addition, a streaming broker acts the same as a messaging broker in terms of message delivery. One microservices send messages to the streaming broker, and one or more other services can subscribe to, consume, and process them. Streaming brokers can deliver the same message to many consumers without the need for replication. Streaming brokers always deliver in the same order the messages are queued. Unlike message brokers, which only act as a message transport, stream brokers additionally act as a data store. One of the most popular streaming broker is Apache Kafka. In spite of all the positive aspects, microservices can't solve all the software problems. They are certainly not so easy and some drawbacks exist. One of the major drawbacks is difficulty in integration testing. Independent services within a microservice based application may be tested in different environments, but to test them together, changes from all the services need to be deployed on one machine. The more the modules, the more difficult it is to integrate services into one project and ensure its efficiency. It is possible that one service accidentally deployed a previous version, which can lead to unexpected response. To set up communication between services is another challenge. In a monolithic application, all the components were part of one code base, so there was no need to set up a separate communication streams. But with microservices, it is an additional overhead. Also, in case one of the services is down and another service is waiting for its response, it can lead to unexpected errors. Moreover, it becomes difficult to monitor states of the services and find out which service is down and causing the issue. Also, each new microservice added to the production deployment comes with its additional cost of new test suites, deployment playbooks, hosting infrastructure, monitoring tools, and adds to operational complexity. Management of multiple databases and transactions can be really cumbersome. The problem of operational complexity may be partially solved by the implementation of new configuration management tools like Docker, which I'll discuss in some another video. Moreover, new tools are being developed, or a lot of tools have already been developed to support microservices. Many global giants have moved their software to cloud and adopted a modern microservices architecture. Netflix is considered to be the pioneer in migration from a monolithic to microservices architecture. At that time, it was a risky move, but the company succeeded, and Netflix paved the way and was later joined by Amazon, Google, IBM, LinkedIn, Nike, Orbitz, PayPal, Spotify, Target, and many others. So this is it for the video, and if you like this video, please hit the thumbs up button and please subscribe to my channel for more videos like this.